All right, so the next topic we need to talk about is really the beginning of the stuff that will take us the rest of the way through the semester. We're going to be focusing on now rotational motion. And so suppose we've got an object that is in rotational motion, like a spinning CD. The velocity and speed at one location on the CD will be different at a different location on the CD because the distance this moves around will be less than this distance in the same amount of time. So the thing, though, that will end up staying the same is the angle. So if it starts here and ends here, then the angle between this and there is the same for the one part that's inside than the part that's outside. And so there's a natural way for us to be able to think about rotational motion that involves the angle through which something moves rather than its distance in meters. So in order to be able to relate the two together, because still we've been dealing with meters and seconds, that a radian is defined as the angle where the arc length is the same as the radius. So if we were thinking about, before we move on from here, there's a terminology thing. If we're talking about, if it's spinning around something through here, so if it spins around like that, this direction that my fingers are on right here, this direction will be called the axis of rotation. So we're going to end up using that term throughout. So the axis of rotation is the line through which something is spinning around. Okay, so 1 radian will end up being that angle such that the radius measured from the center of the rotation out to where you're measuring this point, that it's where the radius here and the arc length around when it would rotate are the same distance. So this distance around and that distance here will end up being the same for 1 radian. And notice, of course, if you double the angle, if it goes around twice as far, then the distance is going to be twice as far too. So they're proportional to each other. And so the arc length, the distance around, will equal the radius times the angle through which it moves, as long as we measure the angle in radians. Now that might immediately think, okay, now we got to change our calculator. We got to change everything to radian mode. It turns out that pretty much all the time we're going to be using this, we're actually not going to end up using trig functions on the number of radians. And so in that situation, it makes no difference computationally whether you have it in degree mode or not. So you might as well leave it in degree mode on your calculator, unless you need radians for some other class. But typically you don't need to worry about changing it to radian mode, but do understand that the angles we'll be talking about in terms of our formulas are often most convenient whenever we end up doing them in radians rather than doing them in degrees or something else. And so your arc length, the distance around, is measured in meters. You'd measure it with, taking a string and you stretch it around and then you measure how long the string is. While your angle is, of course, measured in radians or in some other unit, but radians is the one that's the easiest because the formula is easiest. Your arc length S will be the radius times your angle theta if it's in radians. Otherwise, you have some other factor involved if we use some other unit. So whenever we're talking now about your speed, remember speed is the distance traveled divided by the time it takes to travel if you take it over a short enough period of time. So if we do it over a short period of time, now the distance something travels on rotating surface will end up being an arc length because it's moving in a circle. So it'll be its arc length divided by the time, assuming the time is short enough so that, again, from what we've talked about before, as long as the time is short enough that it doesn't matter, the ratio stays the same whenever you cut the time in half, basically. Same idea as we've had before with velocity in terms of position and acceleration in terms of velocity. So your speed will equal your arc length, which is r times your change in angle, divided by your change in time. So then the radius is not going to change because we're assuming we're moving on a circle. So the distance from it is not going to be changing. So you can factor the r out. It'll be r times the change in your angle divided by change in time. And that ratio, delta theta over delta t, gets a special name. It's called your angular velocity, and it's a lowercase omega. So in order to draw an omega, let me try to do this where it feels backwards. So we end up doing it sort of like that. So think about not a W, but sort of a rounded W like that. So that's how you'd end up drawing an omega. And omega then will end up being your change in angle over change in time if your time is small enough, just like, again, the definitions we've had before. And we finally identify angular acceleration, and angular acceleration is going to be a lowercase alpha. It's the change in your angular velocity over change in time. So to draw an alpha, it depends on what you've done before. That if you have drawn a number infinity, then it would be where you cut off about a piece of that. So if you were tracing it, like I said, I have to do this backwards, so better. So we do it like this. So it would be up. Okay. Pretend like you're drawing an infinity and you leave off the last part. So it's got the little tail sticking out that you can end up seeing what it looks like on there. Sorry, I can't get this the geometry right with the stupid camera. The angular velocity unit, so the angle, of course, is radians. Your angular velocity is change in angle over change in time, so that would be radians per second. Radian is a meter divided by meter, so sometimes you just leave off the radian, so it can be written as a second to the minus 1. Angular acceleration is radians per second squared, which is seconds to the minus 2. That it probably is a better idea for you to keep the angle unit, the radian, in there, but it is optional. But that I will encourage you to leave the radian as part of the unit. But remember that whenever you multiply radians times meters, you get meters. It's not radian meters or something like that. Radian is basically just a dimensionless quote-unquote unit. Okay, so one of the things which dovetails actually into some of the geometry issues we've got. If we end up having an object that's rotating, if you look at it from one side, and I'll rotate it like this, if I rotate it like that, it looks like this is going clockwise. If I move it over here, I rotate it the same way, it looks counterclockwise. Depends on which side of the object you are, whether it appears to be clockwise or counterclockwise. So that term is ambiguous. So we want to end up coming up with a way to describe which direction this is in a way that doesn't have that ambiguity, where we can end up describing it in a unique way. And the unique way of doing it is going to end up involving what we call a right-hand rule. And the right-hand rule is where you take your right hand and let me see whether this is going to work. So, so if this is rotating like this is actually my right hand, even though it appears on my left. If I end up rotating this like this, so if this is spinning like that, then what I do, I take my right hand, if this spins like that, I'll follow the direction it's spinning. So it spins in this way. Oh, so, all right. And that doesn't come out right. So when you do it, it should end up coming out the correct way. In my case, because the camera reverses your orientation, I'm going to actually have to use my left hand to do this, which is awkward. But if I spin this around like this, so it's spinning in this sense, so it spins like that, then the direction I'll want to use is going to be So, okay, if it spins like this, then yeah, it should end. So that gives me the right direction. So it spins around like this. I curl my fingers so the direction that it points is going to end up being to the left. And if you look at it on either side, you'll get the same effect. Again, that's one of the problems with the camera reverses the direction. So in your case, you should use your right hand. If you follow your right hand around, it should give you the right direction. And so that's how we end up giving a unique direction to your angular velocity and a unique direction to your angular acceleration. So acceleration, again, if it's speeding up in a direction, it follows the same direction as your angular velocity. If it's slowing down this rotation, then your angular acceleration is the opposite way. There is a little bit of an aside because we're going to be doing some things that involve right-hand rules as we move forward. There's nothing whatsoever in physics that is specifically right-hand. There's no universal rightiness in the universe that requires you to use it. The reason why a right-hand rule is used is because of anti-left-handed bigotry, which sounds really strange to end up saying it. And again, this was because all these things were done a long, long time ago, so the language ends up following stuff through time. And in order to get a feel for this, the word that you'll end up using if you have an answer on a question, you got 100% on the exam, that what you would say for question 5 is that you would have gotten it right. That's one of the two words that we use for it, and right it's not an accident. It's the same word used for the geometric direction and for it being not wrong. And the other word that's used for it is correct, and co means it goes alongside in some way. So it goes alongside, and rect ends up coming from the Latin rectus, and rectus is in the geometric rightward direction. If you've heard of things like a left-handed complement, right, you end up having all kinds of stuff that is historically anti-left bigotry. By the way, I'm right-handed, so this isn't that, oh my gosh, he's, because I'm trying to be obnoxious about that. That's the way that some of this stuff has happened historically. It's, and you say, well, gosh, okay, at least this was stuff that was a long, 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 long time ago. I believe it was 2016 that there was a high school student, a kindergarten teacher in Oklahoma that ended up, she got kicked out very rapidly after she did this, but it was at a religious school, and that stuff like this tends to last longer in religious stuff than it does outside, and that they ended up at this school, there was a student who was naturally left-handed, and this teacher in 2016 ended up binding the student's left hand behind their back and was ending up berating them and trying to force them to use their right hand to write with. So like I said, that things have changed on that score over time, but it's something that that bigotry has been around for a very, very long time. So that's the reason why we use a right-hand rule rather than left-hand rule. And we're going to see a lot more things that involve using right-hand rules and things like that as we end up moving forward. Again, there's nothing specific on that, but it's, again, one of those, just like with a coordinate system, that once you pick it, you have to stick with it, and we picked that a long, long time ago, so everybody sticks with it into the indefinite future. So anyway, that ends up giving us our early introduction to rotational stuff. And then we're going to end up in the next one looking at rotational big four and that sort of thing. So kinematics with rotation, and then we'll end up in terms of looking in the future. So we'll have rotational kinematics, big four type stuff. Then we'll end up having rotational dynamics, the rotational analog to Newton's second law, and the things that go along with that. We'll then introduce kinetic energy, and kinetic energy will end up requiring us to look at a concept called moment of inertia. So we'll end up looking at moments of inertia, and then we'll end up looking at the analog to momentum, which is angular momentum. So we're going to do a lot of stuff having to do with rotation. Then at the very end, we're going to end up looking at how we combine things having to do with rotational motion, with linear motion, with what's called equilibrium. And so we'll end up taking a look at that. And that basically is going to be what we'll be doing for the rest of the semester. So that gives you sort of a feel for what we've got left. All right, so I will talk to you whenever you end up opening up the next video, but in principle, 2 days later. All right.